This presentation will explain how the state of polarization of a laser can be determined by all optical means using the Kerr effect without relying on physical wave plates or polarizers for detection. First, the generation of frequency sidebands via the Kerr effect is explained. Then, the impact of polarization on the generation of these sidebands is discussed, and a method for recovering the SOP of a laser is proposed. Subsequently, an experimental setup implementing this method is shown, and experimental results are presented. Finally, assumptions, limitations, and potential applications of the work are discussed. If two frequencies of light are launched into an optical fiber, the Kerr effect, which is proportional to optical power, will induce sinusoidal phase modulation. Using the Jacobi-Yang expansion, this modulation can be expressed as an infinite sum of frequency sidebands whose amplitudes depend on the launched optical powers. This short animation demonstrates how sidebands grow as light propagates down a 2 km fiber. Previous models for sideband generation were scalar in nature, but polarization clearly plays a role. For small input powers, the power of the nth order sideband depends on the 2nth power of cosine of alpha over 2, where alpha is the angle between the polarization vectors represented on the Poincare sphere. Experimental data shows that choosing a small alpha value leads to strong sideband generation, while choosing a large alpha value close to 180 degrees leads to weak sideband generation. This result can be exploited to recover the state of polarization S hat of a signal laser. Choosing the first order sideband and a polarization of the reference laser along X hat, we obtain an expression for the power of the first order sideband and a relation between the angle between the two lasers and the first Stokes component of the signal. Repeating this for Y hat, we get two corresponding expressions. Manipulating these two sets of equations shows that the first Stokes component of the signal can be extracted from measurements of optical power for certain choices of reference laser polarizations. Further repeating the analysis for diagonal and circular polarization components yields an expression for the SOP of the input signal recovered by all optical means. The experimental setup for recovering the state of polarization by all optical means consists of 3 segments. The first segment generates 6 reference pulses with equal power spaced 5 nanoseconds apart. They are aligned to have polarizations along the cardinal directions on the Poincare sphere. In the second segment, a continuous wave signal laser is sent through a programmable polarization controller and merged with the reference pulses. A part of the signal light is sampled using a conventional polarimeter for future comparison. In the third segment, the merged signal and reference pulses are launched into a highly nonlinear fiber, where sidebands are generated. Subsequently, the first order sideband is extracted and detected. The relative powers of the 6 pulses coming out are determined, and the SOP of the signal laser is calculated. The polarization controller was used to sweep the SOP of the signal laser, while measuring the SOP using both our method and the conventional polarimeter. Results show good agreement between the two measurements of the state of polarization. By randomly selecting a large number of states of polarization, we find that the angle between the SOPs determined by the conventional polarimeter and the SOP determined by our method is at most 10.22 degrees on the Poincare sphere. In other words, if the SOP of the polarimeter is assumed to be correct, our method will, at worst, determine an SOP within a region of the Poincare sphere, which corresponds to 0.8% of its total area. The model assumes zero dispersion, no attenuation, or birefringence. Imperfect electro pulses used to generate the reference light meant that pulse tails would overlap with neighboring peaks, making it difficult to perfectly align the polarizations. In principle, one could use as little as 3 pulses, though this would make the recovery of the SOP more mathematically complicated. Potential applications of this novel technique for determining the SOP of a laser involve enhanced polarization-based sensing, such as POTDR, new approaches for polarization division multiplexing in telecommunications, and the instrumentation of an all-optical polarimeter for scientific measurements. Thank you for your attention.